Okay, so here we're going to use the ratio test. And we'll line everything up with its friend. All right, so the only factors that have n in them are this part right here, which as we take the limit, that part approaches 1. So the result of our ratio test is 1/5 times the absolute value of x minus 6. Okay, so we're now going to set this guy to be less than 1 and solve for the interval of x values. Okay, so our IOC is basically going to be the interval from 1 to 11. We just need to see which endpoint, if any, are included. So let's quickly let x equal 1. We'll let x equal 11 as well. So when x is equal to 1, our series is 1 minus 6, which is negative 5 to the n, over n times 5 to the n. And this is negative 1 to the n over n. And of course we know this is a conditionally convergent series, so this series converges by the alternating series test, so 1 is included. Now let's let x equal 11, and 11 minus 6 is 5 to the n. So here we get the series 1 over n, which is divergent. It's the harmonic series. So 11 is not included, and therefore our IOC is the interval including 1 but not including 11, and our radius of convergence is half of that length, so that would be 11 minus 1 is 10, 10 over 2 is 5, so radius of convergence of 5. For this one, we could do the ratio test if you wanted, and get your bounds and then plug in the limits of the bounds independently, and you'll see actually that both of them fail, which means we're going to get an open interval here. And the reason I know this is because this is actually directly in the form of a geometric series, so we can just test that R value and strictly set it less than 1, and we know that that's only where this thing is going to converge. Okay, so we'll just solve this inequality here. So that's 2 times the absolute value of x being less than 1, or absolute value of x being less than 1/2, or x being between negative 1/2 and positive 1/2. And like I said, we don't have to test the endpoints manually. You can if you want, but you're going to find that they both diverge, because when we know we have a strict geometric series, you know that when the absolute value of r is equal to 1, the series will diverge. Okay, you may recognize this particular function as the series representation for e to the negative x, okay, which you know to be an entire function. And so you can predict that its IOC will be all real numbers and its radius of convergence will be infinity. So that's all well and good, but let's prove it, and the easiest way to do that is with ratio test. So this is a factorial battle, which resolves to 1 over n plus 1 times the absolute value of x. Okay, now x relative to the limit is a constant. So as we take this limit to infinity of n, we get this algebraic part approaching 0, and 0 times a constant for any value of x, of course, this is going to evaluate to 0. So the entire ratio test evaluates to 0, which is less than 1 regardless of what x is, right? So 0 is less than 1, and therefore the series converges for all x. So the IOC, as we predicted, is negative infinity to positive infinity, and the ROC is infinity. Okay, for this one, probably no surprise, we're going to use the ratio test. Here, conveniently, everything's lined up with its friend, so we'll just reduce. All right, so as we take this limit, what happens to each part? Well, this guy here, that runs off to infinity. What about this one? That one actually goes to e. It's a well-known limit, goes to e. And so we get infinity times e times x is a finite number here. So where does this limit go? Well, if x is equal to 0, that's going to zero out the whole limit, which means we get 0. But if x is anything besides 0, we're going to get infinity out of this limit. So this limit here is 0 if x is equal to 0, or it's infinity if x is not equal to 0. Now, 0 is less than 1, but infinity is greater than 1, which means that this series converges exactly if x equals 0, and it diverges if x is not 0. So we conclude that the IOC is just the interval starting and ending at 0. So we usually just write it as a singleton set using set notation, but it's not wrong to say the interval starting at 0 and ending at 0, which of course you have to include 0, so put brackets there. It's not wrong to write that, but it's a little weird. And the radius of convergence is 0. So if we're being asked to find a Taylor series centered at A, and A is not 0, which otherwise would be a Maclaurin series, then we pretty much have to just go through the steps of taking a succession of derivatives until we can get a pattern for the nth derivative at A. In other words, we're going to use this definition. So let's take a bunch of derivatives. So we'll start with the 0th derivative, which is just the function. First derivative. Second derivative. And so on until a pattern emerges. And try to resist, as usual here, the temptation to reduce these numbers, because you might lose some of the information that you're looking for. So usually I go to about 4th or 5th derivative before things really start kind of being obvious. Okay, so I think we have enough information to write down the nth derivative at x, and then we'll just plug 2 in, which is our center value at a equal 2, into this formula for the nth derivative. So to be clear, this is the n equals 4 case, this is the n equals 3 case, this is the n equals 2 case. So it looks like we have a bunch of negatives, and it looks like we have in each case exactly n negatives. Like when n equals 4, we have 1, 2, 3, 4 negatives. When n equals 3, we have 1, 2, 3 negatives, which means we can put negative 1 to the n here. Negatives are handled. We seem to have some sort of factorial structure developing, although it's not n factorial, because when n is 4, we have 5 factorial, and when n is 3, we have 4 factorial. So it looks to me like that would be n plus 1 factorial. Okay, and of course we have x to some negative, and it looks like that negative is 2 more than n, because when n is 4, it's negative 6, and when n is 3, it's negative 5. So there's our pattern for the nth derivative, and now we're going to look at plugging in our a value, which in this case was given as 2, because 2 is the center of our Taylor series. So this is going to be -1 to the n plus 1 factorial, and then 2 to the negative n plus 2. Okay, which we can write as 1 over 2 to the n plus 2. All right, so now we can go back to our form for the Taylor series, plugging 2 in, x minus 2 to the n, and we'll just replace the nth derivative at 2 with that formula that we found. Except I'm going to put the 2 to the n plus 2 in the denominator. All right, and now we just take a look at it and see if anything kind of reduces, and we do have a factorial battle that can be resolved. So that looks like it would come out to n plus 1 over 2 to the n plus 2 times x minus 2 to the n. And that's our final answer. So that equality holds over the interval of convergence of the series. Okay, once again, if we're finding a Taylor series and it's not centered at 0, which would just be a Maclaurin series, then we have no choice but to appeal to the literal definition by taking a succession of derivatives. So let's do that. So remember, we're looking for a pattern here. So I think it should be pretty clear that each time we're taking a derivative, an ln of 2 will emerge. So we can probably just guess now that the nth derivative at x will be 2 to the x times ln 2 to the n. And therefore, what we're really after, which is the nth derivative at 1, where we're centering, that'll be 2 times ln of 2 to the n. And so according to the Taylor series formula, this function is equal to the following form: nth derivative at a, which is in this case 1, over n factorial x minus 1 to the n. And that is equal to n equals 0 to infinity of the pattern we just found, which is 2 times ln 2 to the n over n factorial x minus 1 to the n. And we ought to take a quick glance to see if anything reduces, if there's a factorial battle to resolve or anything. And actually, in this case, there is not. So that is our final answer. Okay, when we're asked to find a Maclaurin series, we could go through all the motions of working out a Taylor series and just let a equal 0. But usually the intent is for you to base this on a known Maclaurin series and just make a couple of substitutions as needed. We can see that x over 3 plus x is just x times 1 over 3 plus x. So all we have to do is find a Maclaurin series for 1 over 3 plus x and then multiply our answer by x. And to do that, we can factor a 3 out of the denominator, giving us 1 over 1 plus x over 3. Okay, and we can write that as 1 over 1 minus negative x over 3. So this is now the form 1 over 1 minus stuff, which we know is just the sum of that stuff to the n, from n equals 0 to infinity. So the rest of this is simply just cleaning it up. So we have x over 3, n equals 0 to infinity, negative 1 to the n, x to the n, 3 to the n, and if we move the x over 3 inside, that will increment the power of n for each of the x and the 3. So we have negative 1 to the n, x to the n plus 1 over 3 to the n plus 1. And you can write it that way, or you can start the series at 1 and write it like this if you want. might be a little cleaner. I think that second way is a little cleaner, but both are perfectly acceptable answers. Okay, for this one might be tempted to take the Maclaurin series for sine, which is well known to be this one, and then just square both sides, giving us sine squared on the left is equal to the square of that series. Now, while that's not incorrect, what would be incorrect would be to start just squaring all the individual terms, because that's not how squaring a sum works. This would, in fact, be an infinite FOIL, right? So that would be sine of x, we know, would be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. And if we're squaring that, we'd actually be foiling this monster. Right. Now, there actually is a technique for doing that. It's called a Cauchy product. But that's not at all the easiest way to deal with this. So we're not going to do that. So what can we do instead? Well, we're going to use a trigonometric identity. Let's recall that sine squared of whatever is 1/2 1 minus cosine of 2 times the whatever. So in this case, g of x, which is sine squared of x, is equal to 1/2 minus 1/2 cosine of 2x. And cosine of stuff is negative 1 to the n times that stuff to the 2n over 2n factorial. So we have 1/2 minus, let's move the 1/2 inside and distribute the 2n. So we get negative 1 to the n, 2 to the 2n minus 1, x to the 2n, all over 2n factorial. Okay, and that's a perfectly good final answer. But I think with the negatives subtracting, let's just move the negative inside. So it's a little nicer if we write this as negative 1 to the n minus 1, 2 to the 2n minus 1, x to the 2n over 2n factorial. Now the one above it is correct as well, but it's a little nicer to just push that last negative in and offset the negative 1 power. Okay, so here we're going to just use the fact that we know e to the x is this one here. And so we can say, well, x e to the negative x squared is therefore equal to x times the Maclaurin series for e to the x with x replaced by negative x squared. Okay, so this is x times n equals 0 to infinity, and let's distribute that n. We get negative 1 to the n, x to the 2n over n factorial. And now if we push that last x inside, we're going to get x to the 2n plus 1 over n factorial. Okay, for this one, we're going to use the fact that we know that ln of 1 plus x is n equal 1 to infinity, negative 1 to the n minus 1, x to the n over n. All right, and we will write out ln of 1 plus x over 1 minus x as ln of 1 plus x minus ln of 1 minus x. And for this one, we can directly convert that into its well-known Maclaurin series. And for this one, we almost can, just by replacing x with negative x. So let's see what happens. Okay, so we have a difference of two series, which we can probably put together by working them out term by term. But before we do that, let's clean up that right-hand series. We can definitely do something with this. One of those is negative while the other one's positive at any given moment. So they multiply together to always give you a negative, which will combine with the minus that's in front of that series, becoming a plus. So this is just this, n equal 1 to infinity, negative 1 to the n minus 1 x to the n over n, plus n equal 1 to infinity, x to the n over n. All right, so now to combine these two series, we should probably work them out term by term. So that first series works out the following way. We'll plug 1 in, and we're going to get x to the 1 over 1. So we get x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5 minus x to the 6 over 6, etc. And we are adding to that the terms of the other series. So when we plug 1 in, it's actually going to be the same terms, but without the alternating part. So we're going to get x plus x squared over 2 plus x cubed over 3 plus x to the 4 over 4, etc. And by rearranging the terms, we can see lining up these even terms are going to cancel, and the odd terms are going to accumulate. So we get 2x plus 2/3 x cubed plus 2/5 x to the 5 plus probably 2/7 x to the 7, etc. Okay, so now we have really clear terms of a series. We can collapse this back down into a single sigma notation. So this would equal, say, you can start your n wherever you want. I'm going to start it at 0 here. And it looks like we have a 2 over 2n plus 1 times x to the 2n plus 1. Final answer. Okay, well, inverse tanh is, according to the fact that its derivative is 1 over 1 minus x squared, means that inverse tanh will be the antiderivative of 1 over 1 minus x squared. And so what we're going to do is convert this guy to a power series and then integrate that one. So here we have c plus the antiderivative of, well, we know that 1 over 1 minus stuff gets converted to that stuff raised to the n. So this is x squared to the n. So that would be x to the 2n. And we can distribute the integral into the sum and then integrate x to the 2n. So we get c plus n equals 0 to infinity of x to the 2n plus 1 divided by 2n plus 1. And that's what inverse tanh is. However, we actually need to establish what this c value is, because inverse tanh has a very specific Maclaurin series, and the first term of it can't just be c. So to determine c, we're going to plug in the center of the Maclaurin series that we found, which of course all Maclaurin series are centered at 0. So we're going to let x equal 0 here. Okay, which means on the left we get inverse tanh of 0, and on the right we get c plus, well, if you plug 0 into x, every single term of that is going to evaluate to 0. So c is simply the inverse tanh of 0. Okay, well, what the heck is inverse tanh of 0? Well, if you recall, tanh of x is sinh of x over cosh of x. And you can therefore see that tanh of 0 is equal to 0. And therefore, inverse tanh of 0 is equal to 0. So here we can see that inverse tangent of 0 is 0, and so therefore c is equal to 0. And so inverse tangent of x is just n equals 0 to infinity, x to the 2n plus 1 divided by 2n plus 1. And you may notice that that's very similar to the power series for inverse tangent. The only difference is that for the power series for inverse tangent, there's an alternating negative 1 to the n factor, but for inverse tangent, there is not. Okay, so of course, when we're converting to a Cartesian equation, one way is simply to isolate t in one of the equations and then substitute into the other equation. So for instance, here we could solve x equal tangent of t for t by writing t equal inverse tangent of x. Now, this will generate an angle t between negative pi over 2 and positive pi over 2, and that happens to coincide with the bounds given for t in the problem, so this is perfectly safe. But you'd have to be very careful if the bounds for t were, say, given as 0 to pi, all right? So no problem. Now we can conclude that y is equal to secant squared of inverse tan of x, and we can reduce this. Okay, well, how do we reduce this? You could draw a triangle, and we know that x is equal to tangent of t, so our angle here is t, and we can label the sides so that x is tangent of t, and using the Pythagorean theorem, we could find the missing hypotenuse here, which would be radical 1 plus x squared, and now we can read off of this any trig function we want, secant, cosecant, whatever. Here what we need is secant squared, so that's going to be the square of secant, and secant will be 1 plus x squared under a radical over 1, and that's being squared, of course, so we get that y is equal to 1 plus x squared. And that is the correct answer. Now that was a perfectly good way to do it, and we got the right answer. However, I want you to note that if there is trigonometry, it's often easier to just start with an identity that relates the trigonometric functions that you're dealing with. So I am going to erase everything, and instead we have x equal tangent of t and y is equal to secant squared, and let's just recall the identity 1 plus tangent squared of t equals secant squared of t, right? The mnemonic for that is I tan secretly. And converting, we know that tangent is x, so this is 1 plus x squared is equal to secant squared, which is y. And so we're done. So of course, our answer is y equals 1 plus x squared. The second part of this was to sketch the graph, and we know that that would simply be a parabola shifted up 1 unit. Okay, so we do have to indicate the direction that the curve is tracing as t increases. So when t is a negative number, we know that x is also negative, and y is of course always positive. So we can see that it's growing this way. As t moves from negative pi over 2 to positive pi over 2, the angles move from the fourth quadrant to the second quadrant, and therefore the tangent of them move from negative values to positive values. So x moves from negative to positive here. So there we are. Okay, well, we know that dy dx is equal to dy dt divided by dx dt. And we know that the second derivative with respect to x of y is equal to the derivative with respect to t of dy dx divided by the derivative of x with respect to t. Okay, so we have our work cut out for us. We're going to need dy dt and dx dt. So dx dt is, of course, just e to the t. and dy dt is cosh of t. So therefore, dy dx, which is dy dt divided by dx dt, is cosh of t divided by e to the t. And cosh of t is e to the t plus e to the negative t all over 2. So multiplying everything by e to the t, we get e to the 2t plus 1 over 2 e to the 2t. So this is our dy dx. Since we know we're going to plug a t value in, let's write this in a form that minimizes the number of places we need to plug t in. So I'm going to do one quick simplification where we split the fraction up into simply 1/2 plus 1 over 2 e to the 2t. So now we can plug ln of 2 in, and there's only one place to plug it in. Our dy dx is equal to 1/2 plus 1 over 2 e to the 2 ln 2. Well, 2 ln 2 is, of course, ln of 4. So e to the ln 4 is, of course, just 4. So this is like 1 over 2 plus 1 over 2 times 4. All right, or 1/2 plus 1/8, which is 5 over 8. So that's what dy dx is at the moment we're interested in. Now we need the second derivative. So that would be derivative with respect to t of the first derivative, which I'll write like that because it's a little easier to take a derivative that way. And that's all over the derivative of x with respect to t. So this is going to be simply negative e to the negative 2t, all divided by e to the t. So that would be negative 1 over e to the 3t. That's what d squared y over dx squared is. And then at the point in time when t is equal to ln of 2, we get negative 1 over e to the 3 ln 2. And 3 ln 2 is, of course, ln of 2 cubed, which is ln of 8. And e to the ln 8 is 8. So this is just negative 1 over 8. Okay, here we're going to use the Arclength formula for parametric equations, which looks a lot like the Arclength formula for Cartesian equations. So we just need the derivative of x with respect to t and the derivative of y with respect to t, and we're just going to load those right where they go, and then we'll evaluate that integral. So dx dt is 1, and dy dt is 1 over secant of t times the derivative of secant. So that would be tangent of t. So therefore L is the integral from 0 to pi over 4 of 1 plus tangent squared of t dt. 0 to pi over 4 of the square root of secant squared dt, because 1 plus tangent squared is secant squared. And the square root of secant squared is the absolute value of secant, except these t values are all in the first quadrant, so secant's positive. So we're just integrating secant from 0 to pi over 4, which we know to be ln of absolute value of secant plus tangent. And so we'll just plug in pi over 4 and 0. So we get ln of secant of pi over 4, which is rad 2, tangent of pi over 4, which is 1, minus ln of secant of 0, which is 1, plus tangent of 0, which is 0. So that right-hand term is just ln of 1, which is 0. So our final answer is ln of 1 plus rad 2, which is a positive number, so we don't need the absolute value. And that's our length. Okay, when we're converting from Cartesian to polar coordinates, we are going to use the following formulas, that r squared is x squared plus y squared, and tangent of theta is y over x. We get to choose whether we want our r to be positive or negative. Correspondingly, we need to select our theta so that the quadrant is correct, given the quadrant of the original point. So, for instance, 3 comma negative rad 3 is in quadrant 4, which means if we choose a positive r value, we need our theta to be in the fourth quadrant. If we decide to choose a negative r value, then we'll have to choose our theta to be in the second quadrant so that we point ourselves into the second quadrant, that's theta, and with a negative r value, we kind of back into the fourth quadrant where this point actually lives. So, all right, let's start by finding an r value. So r here, r squared is x squared plus y squared. Okay, so that would be 9 plus 3, which is 12. So we can choose r to be whatever you want, plus or minus the square root of 12. Okay, and let's just choose r to be the positive version of this. So therefore, theta must be in quadrant 4. Okay, so now we know that tangent of theta is y over x, so that would be negative rad 3 over 3. And all we have to do is just pick a theta value in the fourth quadrant that satisfies that. And of course, if we go with something like negative pi over 6, we know this is going to work. But you could also go with 11 pi over 6 or anything coterminal to those, as long as it's a fourth quadrant angle whose tangent is negative rad 3 over 3. So we can declare that our specific r theta that we found is 2 rad 3 comma negative pi over 6. Okay, for part B, we're going to, same reasoning here, but let's note that negative 1, negative 2 is in quadrant 3. Okay, which means that if we choose an r value that's positive, we need a corresponding theta value that is in the third quadrant. If we choose an r value that's negative, we can go with a first quadrant theta value. So r squared is x squared plus y squared. So that would be 1 plus 4. So r squared is 5. So we can choose plus or minus root 5 for r. Okay, let's go with r equaling rad 5, which means that our theta must be in quadrant 3. Okay, well, we know that tangent of theta is y over x, so that would be negative 2 over negative 1, which is 2. Now, if we try to think of ratios involving tangent that equal 2 on the unit circle, we're going to come up short because that's not one of our special ratios for tangent, okay? Which means we have no choice but to use inverse tangent. So we can say that theta is equal to inverse tangent of 2. The problem here is that we're not done, because inverse tangent of 2 generates a first quadrant angle. All right, so we already decided that since our r was positive, that we must choose theta in the third quadrant. So we can either change our mind about r and go with negative root 5 and keep theta the way it is. Okay, so one possible answer would be to go with negative root 5 and inverse tangent of 2, right? So inverse tangent of 2, first quadrant angle, but we're moving backwards in that direction, which will actually put us in the third quadrant where the point negative 1, negative 2 is. Alternatively, if we do insist on keeping that positive rad 5, then we'd have to go with the angle that's exactly opposite to inverse tangent of 2, so the third quadrant equivalent to it, and we'd be adding pi. So we just go like pi plus inverse tangent of 2. Now you could subtract pi from it and do just as well. Okay. Now why don't we call this guy here A, B, and C. And so we'll start by plotting A. So we first point ourselves in a direction of 3 pi over 2, which is this way right here. And we're going to move 2 units in that direction from the origin. So that would be 1, 2 right here. So there's point A. All right, good. For the point B, we are going to point ourselves in a direction of pi, which is this way. And pointed that way, we are now going to move -1 units from the origin. So that would actually have us jumping out to this point over here. Okay, so yes, that's what -r values will do. And for point C, we are going to point ourselves in a direction of -pi over 6, which would be that way right there. And we're going to move 2 root 2 units in that direction. That is positive, so we'll move into the fourth quadrant. And 2 root 2 is about 1.4, so 2 of those is about 2.8. So that would be point C right about there. Okay, when we're converting from a polar equation to a Cartesian equation, it usually means we're going to use something like this. X is equal to r cosine of theta, and y is equal to r sine of theta. However, we do have an r squared, and we know that x squared plus y squared is equal to r squared. So that may be helpful. We could, for instance, start by replacing r squared with x squared plus y squared, and then figure out what we're going to do with sine of 2 theta. However, I'm actually going to work with the sine of 2 theta first because I have a hunch that we're going to need both those factors of r. So let's also recall that sine of 2 theta is 2 sine theta cosine theta. And so r squared sine of 2 theta equaling 1 unwraps to r squared times 2 sine theta cosine theta, which equals 1. And we could rearrange these factors to 2 times r sine theta times r cosine theta. And of course, r sine theta is y, and r cosine theta is x. So this particular exercise didn't give the imperative to isolate y, but we could just by saying y is equal to 1 over 2x. Okay, for these, I generally think it's a good idea to start by sketching them on r theta axes. So we can see this one has a vertical shift of 2 units and an amplitude of 2 units. And it's an upside down sine wave, so it's going to start here. All right, and it has a period of 2 pi, so that would be a 2 pi there, pi, 3 pi over 2, and pi over 2. All right, and we can also see this has a range of 0 to 4 because of the vertical shift in the amplitude, which means that when we draw this thing on a polar grid, we will need 4 concentric circles, or we can use 2 concentric circles and label each one as 2 units. Also, we can see that while our curve makes contact with r equal to 0, which would correspond to the pole of the polar grid, it's not going to cross the pole. All of our r values are non-negative. So that means when we're considering an angle in quadrant 3, for example, we're actually going to be drawing in quadrant 3 because the r values will be positive. So let's get a polar grid in here. Now this one has 3 concentric circles, so I could either label like 2 and 4, and that'll be enough to catch the whole thing, or we could draw in one more concentric circle, and why not? Let's do that. Okay, so 1, 2, 3, 4. All right, so now we're going to just walk through checking angles between 0 and 2 pi and using the function to consult the r value and then plotting that r value. So starting with theta equal to 0, which is that direction, we can see that r is equal to 2. So our first point will be right there. Okay, next is pi over 6. So sine of pi over 6 is 1/2. 2 of 1/2 is 1, so 2 minus 1 is 1. Okay, next is pi over 4. Sine of pi over 4 is rad 2 over 2. 2 of those is rad 2. And remember that rad 2 is about 1.4. So 2 minus rad 2 is about 2 minus 1.4, which is about 0.6. Okay. Next is pi over 3. And sine of pi over 3 is rad 3 over 2. 2 of those is rad 3. 2 minus rad 3 is about 2 minus 1.7, so that's about 0.3. Okay, and pi over 2, well, we can see that r will equal 0 there. Sine of pi over 2 is 1, so 2 minus 2 is 0. All right, so here we are getting some kind of a curve. Looks like that for now. We also know by the presence of the sine function in here that we are expecting to get symmetry over the y-axis. Okay, which means that we're actually going to get exactly the same points here. All right, very good. So why don't we plug in this point right here, which is 7 pi over 6. Sine of 7 pi over 6 is negative 1/2. 2 of those is negative 1. 2 minus negative 1 is 3. So this actually puts us at a 3 there. All right. Next is 5 pi over 4. Sine of 5 pi over 4 is negative rad 2 over 2. 2 of those is negative rad 2. 2 minus negative rad 2 is 3.4. So that's about here. All right. Next is 4 pi over 3. Sine of 4 pi over 3 is negative rad 3 over 2. So this is like 2 plus rad 3. So that's like 2 plus 1.7, which is about 3.7. All right, and finally, let's plug in 3 pi over 2. Sine of that is negative 1. So this is like 2 minus negative 2, which is 2 plus 2, which is like 4. Okay, and again, by the symmetry, we are expecting those points there. And so I think we're ready to connect the dots here. And what we get is a nice little cardioid. Very good. All right, as usual, I think it's a good idea to start these ones by sketching them on r theta axes. So this is 2 cosine 2 theta. So there's no vertical shift, but we do have an amplitude of 2 units. Let's just draw one typical phase of cosine, and we can see the period here is 2 pi divided by that coefficient. So it's a period of pi. So that means this is pi here, pi over 2, pi over 4, and 3 pi over 4, amplitude of 2. All right, so what do we know from looking at this graph? We know that we only need 2 concentric circles because the graph is never more than 2 units away from 0. Also, we can see that for a good portion of this graph, we will be sketching on the opposite side of where our angle is pointed because our values are negative between pi over 4 and 3 pi over 4. Okay, And finally, by the presence of the cosine, we are expecting there to be symmetry over the x-axis. So let's paste in a polar grid. All right. So let's start with considering theta equaling 0, and we can see that when theta is equal to 0, r is equal to 2. So there we are. Now let's consider the case when theta is equal to pi over 6. So that doubles to 2 pi over 6, or pi over 3. Cosine of that is 1/2, and 2 of those is 1. So at pi over 6, r is equal to 1. At pi over 4, we can actually see that our r value will be 0 there by looking at our cosine curve above. Or we could just evaluate at pi over 4, 2 of those being pi over 2, and cosine of pi over 2 being 0. So this is 0. Okay. So what we have is this thing going through the origin, but it's going to go through the origin at an angle of pi over 4, and that's very important. And it'll go through these points here. All right. So this is going to be the leaf, or part of the leaf of probably some kind of rose curve, which tends to happen when you have a trig function of a multiple angle. So, all right, let's carry on. Where did we leave off? Well, at pi over 3. Okay, so 2 times pi over 3 is 2 pi over 3. Cosine of 2 pi over 3 is -1/2, which doubles to -1. So while we're pointed in a direction of pi over 3, we are actually sketching -1 here, which is right there. Okay, our next direction that we're pointing is pi over 2. And cosine of 2 pi over 2, which cosine of pi is -1, which doubles to -2. So while we're pointed up this way, we're moving -2 units, which actually gets us to over here. Okay, and so again, this comes out of the origin at an angle of pi over 4, which is the angle it went through, and it's going to come around like this. Okay. All right. And we'll do a few more, and then we'll take advantage of the symmetry that we have. So let's check this guy here, which is 2 pi over 3. That doubles to 4 pi over 3. Cosine of 4 pi over 3 is -1/2. And 2 times -1/2 is -1. So while we're pointed in the direction of 2 pi over 3, we are going to drop a point right here at -1. So we've gone backwards a unit. And now we are at 3 pi over 4, which we can also see from our initial sketch that our r value will be 0 there, and that's also no surprise. So this is going to come in to the origin at an angle of 3 pi over 4. All right. Now our next one is 5 pi over 6, which doubles to 5 pi over 3, whose cosine value is now positive. It's 1/2, doubled to 1. So here we are. And now let's plug in pi. So cosine of 2 pi is 1, which doubles to 2. So here we are. All right, so this comes out of the origin at an angle of 3 pi over 4. And it's going to come in like this. Okay, and now let's just take advantage of the vertical symmetry we're expecting and kind of finish this guy off. All right, and what we have here is a 4-petaled rose. That's very nice. Okay, we seek the area within 1 petal of the 4-petaled rose. I've only sketched 1 petal, that's all that's needed. So we could find this angle and this angle, and then integrate from one of them to the other one, the lower one to the upper one, for instance. Or we could find this angle, which is clearly an angle of 0, and then find this angle, and then integrate from 0 to that other angle, and then double our answer. And I think we should just do that. So again, remember, areas are reckoned as emanating out of the origin. So if we're integrating from 0 to that theta, which we actually know from problem 12, that's just pi over 4, because we happen to just sketch this guy, if you're doing the videos in order, then we know that we're going from theta starting at 0 to theta ending at pi over 4. Okay, but if we're not quite sure about it, we can find that bound by solving r equals 0, which is cosine of 2 theta equals 0. And that would mean that 2 theta is pi over 2 plus a multiple of pi. So theta would be pi over 4 plus a multiple of pi over 2. And of course, all we care about is the pi over 4 part. So that's this guy, pi over 4. So now we're going to use, of course, the formula alpha to beta 1/2 r squared d theta. So in this case, we're going to go 0 to pi over 4. But let's double our answer. So, and that's 1/2 r, which is cosine of 2 theta, quantity squared d theta. So there's our setup. Well, it's nice that the 2 and the 1/2 are going to cancel. And we just have cosine squared of 2 theta d theta, which of course we know to use this identity here. 2 theta doubles to 4 theta. And we can now integrate this. That goes to 1/2 theta plus 1 over 8 sine of 4 theta. Theta starts at 0. Theta ends at pi over 4. And this is 1/2 times pi over 4 plus, well, when we plug pi over 4 into theta, 4 of those is pi, sine of pi is 0. And then plugging 0 into those will obviously make 0 as well. So we just get an answer of pi over 8. All right, so typically when it's an area between two curves in polar coordinates, we're going to need two integrals that are either being added or subtracted. And in this case, it'll be subtracted because we're going to look at the area under the cardioid starting from 0 radians and increasing all the way up to pi radians. And then we're going to delete the area under the circle from 0 radians to pi over 2 radians. All right. So we can see that first by solving where this particular function, 1 plus cosine of x, or theta, is equal to 0. So cosine of theta is equal to -1. In this case, theta will equal pi plus everything coterminal to it, but we just worry about pi here. Okay, so we can see that our area is going to be the integral from 0 to pi of 1/2 times 1 plus cosine theta squared minus, now we're going to subtract the integral of the circle, and if we set this guy equal to 0, we get cosine theta equals 0. Of course, that tells us that theta is pi over 2 plus everything coterminal to that. So, all right, so this is going to be 0 to pi over 2, 1/2 2 cosine theta squared d theta. And since this was a setup only, there's our final answer. You don't have to FOIL this binomial here. You don't even have to square the 2 and divide by 2. I mean, obviously this very much simplifies, but for setup only problems, it's just fine to not simplify. In fact, the non-simplified version is often easier at a glance to see the elements that make up the problem. So There we are. All right. So for this one, we should probably see where they intersect. Theta equals, we're not sure yet. And we're going to present this in two integrals being added together. The first one will be this particular orange slice right here, that bottom part, which is the integral starting at angle 0 and ending at angle whatever that theta turns out to be. And we're integrating along the larger circle, that upper one, rad 3 sine theta. And then continuing, we will integrate starting at whatever that theta value is and integrating all the way up to, looks like pi over 2 on the smaller circle, the cosine circle there. So really, we just need to figure out what that theta is. And let's just figure that out by equating the two functions. Okay, so we get tangent of theta is equal to rad 3 over 3. So theta is equal to pi over 6, or, 7 pi over 6. But let's not worry about that. This is clearly the one we want, which is pi over 6. So now we can see that our area is going to be the integral from 0 to pi over 6 of that larger circle, the upper one. So that'll be rad 3 sine theta squared d theta plus the integral from pi over 6 to pi over 2 of cosine theta quantity squared. And there we are. Okay, so here we only need one integral, and it's just going to be the bounds of that one inner loop of the limicon. So it's really that angle and this angle that we need. And yes, those are pointed in the opposite direction from the loop of the limicon in there. If we were to draw a wave, the inner loop of the limicon corresponds to the part of the wave that dips below the axis. Okay, so we just need to solve this guy equal to 0, and you're going to see that we get a third and a fourth quadrant angle result. Okay, and that's because sine is negative here, clearly. Can't be first or second quadrant. So we know that 7 pi over 6 is a solution, and we also know that 11 pi over 6 is a solution. So that must be these guys here. Okay, which means that our area is going to be the integral from 7 pi over 6 to 11 pi over 6 of 1/2 times the function squared d theta. You also could have done like 7 pi over 6 to right here, 3 pi over 2 if you wanted, and then doubled your answer, right? So we really would have had only the left or the right side of that joule in the middle, and you would have gotten the correct answer. Ultimately, this is a setup only, so you would have been correct with your slightly different looking setup as well. Here we are.